Hello. Hi, everyone. It's my pleasure to be here today. I want to first and foremost say thank you for having me. I want this to be as understandable as possible. So if I am saying some weird jargon up here, just like wave your hand and yell and ask me a question, and I'll be glad to try to answer it. I am coming from the Hershey Medical Center. I'm coming from the College of Medicine as part of the Medical College of Penn State University. And I'm going to talk about some of my work with brain-computer interfaces. It segues nicely from Elisa's talk earlier, which talked about, where she talked about a lot of different available assistive technologies. This one's kind of on the horizon. You won't see many people using brain-computer interfaces in their home, and I'll explain where they might be going in the future. So I'm going to first define what a BCI is. For those of you who haven't been in one of my studies, it might be a little opaque to you what a brain-computer interface is. I might say BCI just to make it easier on myself to mean brain-computer interface. Some of my earlier research focused on what the barriers to implementing BCI are, and then we're trying to implement some solutions to getting around those barriers. I certainly, after this morning's talk, don't need to labor on this, but I do sometimes present to an engineering crowd who doesn't know ALS from acne. ALS is a motor neuron disease which, most importantly to me, affects movement and speech, because that's the reason BCI is warranted. When you lose the ability to communicate, you need alternative methods for communication. And officially, we call these augmentative and alternative communication. Elisa talked about a number of these methods, which range from communication boards to iPads to your eye tracking systems. And Paisan gave a nice talk about a completely different type of assistive communication technology. So the reason we need AAC, and in particular BCI AAC, so brain-computer interface assistive, augmentative, and alternative communication, is because it has a potential to improve quality of life. Loss of communication can be devastating to an individual, so this ability to keep a communication pathway open is necessary. It factors into decision-making processes all throughout the disease course. And the inability to communicate with the environment and people around them is often the biggest fear of patients. Eye gaze systems, although they are wonderfully useful, have a tendency to fail after some period. So I've got 4 pictures of some famous, some not famous individuals using different types of assistive technologies. One of them is using a BCI, and that would be this woman over here. Doesn't look like they're doing anything with her brain, but as I'll describe a little bit later, this person has volunteered for a research study where they've implanted an electrode into her head, and they're recording her brain activity that way. Steve Gleason, a little more famous, he uses an eye tracking system on a daily basis to communicate. Stephen Hawking had really used a cheek sensing system for a while before he passed, and that was his optimal way of communicating. And then, as Elisa showed before, you can use a head mouse as well, which is what this man is using. So they look a little similar, right? They've all got computers in front of them and big bulky things, but they're all using very different communication methods.
Yeah, Andrew, I'm Jeff from the association. I've been around long enough to have seen Scott Mackler, whose name I assume you are aware of.
I'm aware of, yeah.
And as I remember the description of the actual equipment, it was some type of a helmet with all kinds of things together. So the device itself, are you able to articulate how that has changed over the years to today for the actual equipment?
We still use those helmets, so I'm hoping my next slide will help define that.
Okay.
So the needs of a brain-computer interface, you need a brain, which most of us have, and you need a computer. And then there's what I do is I record the activity of the brain using one of those helmets, and we call it an EEG cap, technically. But it records the electrical activity that we record at the scalp level. It's the accumulation of 1 billion neurons firing in your head, and we're kind of just measuring a little electrical potential. The person using the system has to self-generate some sort of intent. They've got in their head, present something or give an intent that they want to perform some sort of action. The processing of that signal has to occur in real time, and then the user's got to get feedback on what the system interpreted they were trying to spell. So those are the four kind of components of a BCI, and classic BCIs are the ones you see in movies, I think, where Avatar being a good example, where a person is just hooked up to a system and they're fully controlling this person in a digital world or something like that. There are examples of this, of course, in our research as well. This is distinguished from what we call passive BCIs, or the one I've shown here on the screen is like a monitoring system for vigilance during driving. It's also distinguished from things like cochlear implants and deep brain stimulators in that they're typically not intentionally modulated by the user. It's not converting their intent into something. They are systems that record or stimulate the brain, but they're not BCI systems. And then sometimes you'll see things advertised on TV where they say you're controlling things with your brain, but typically those aren't actually recording your brain. This is a picture from me in graduate school. This is one of those caps that it might have looked like Scott Mackler was wearing. But I'll go over two of the ways in which we take brain data and convert it into communication. The first one is the P300 system, which Scott used during his time with the Wadsworth group, I think, up in New York State, who worked with him. The P300 is an evoked potential that occurs when you see a target that you're looking for amongst a group of non-targets. So how we elicit this is we show the person a grid of letters, and the letters are flashing. And I think this was a video, but it's not working. So the letters are flashing in a kind of a checkerboard or a row column manner. And the person is focusing on the letter they want to spell. And when they see their letter being presented or flashed on the screen, it elicits this P300, which is this positive potential. EEG is weird because they reverse everything. But let's say negative potential that occurs only when that person saw a G, for example. For every other letter that flashed on the screen, they don't get that P300 potential. So we spell by detecting which letter evoked this blip on their EEG signal. The other type of system, which is very popular, and I'll talk about a little bit, is the sensory motor rhythm BCI. We all have oscillations going on in our brain, and in our motor cortex, those oscillations are called sensory motor rhythms. If I were to move my hand like this, the sensory motor rhythm and the contralateral arm area of my brain would change, it would decrease. That oscillation would go from big oscillations to nothing. Now the neat thing is when I imagine that same movement like I'm doing right now, I'm not performing it, but I'm imagining it, we get the same decrease in that power. So depending on where we're recording and what area of the motor cortex we see these changes in the sensory motor rhythms, we can decode whether a person is imagining moving their left arm, their right arm, their foot, their tongue, and this will work as well as a method for control. And this person in this video, which isn't working, is moving a cursor around the screen based on imagining squeezing their hands and moving their feet. So there's been some pretty neat advances in the field of BCI technology, which has, it started in, depending on where you'll consider starting, from the 60s to the 80s, to the point at which we can control computer cursors in 3 dimensions using our brain activity. In the case of this publication that was put out by that group that worked with Scott Mackler. Now I should say this was done in a healthy individual, so I'll get to the difference between healthy individuals and what we might experience when we record from people who have a neurodegenerative disease. But a few more cool examples before then. People have used these to express themselves artistically, using a P300 potential to make art on their computer. And then some maybe not so useful ones where the person is using to control a drone using their brain activity. They're controlling it to turn left and right by imagining squeezing left and right hands, and they're controlling it up and down by imagining both hands or not imagining movement of their arms at all. Now, I showed you the picture of the woman before. This is her in publication form. This is a group from the Netherlands who implanted these electrodes for this woman who had advanced ALS, and she was using that P300 Speller to communicate. And that's one of the, I would say, one of the most recent examples of how far we've come with BCI technology. Another group out of Brown University and Stanford have also implanted electrodes into patients in order for them to use sensory motor rhythms to control the manipulation of a computer. And then this was a really famous one. It showed up in 60 Minutes, I think, twice, from a group in Pittsburgh who was also using sensory motor rhythms recorded from a woman to control the robotic movement of an arm. So these are all examples of kind of where the field has, the basis of the field, and then where some of the more exciting results are coming from. I'm going to talk a little bit about my research, though, and my motivation, a lot of it lies in this chart here. I'm showing communication rates. And for a healthy individual speaking, they can communicate at around 2,000 bits per minute, and a bit is a little bit of a piece of information telling, for example, yes versus no. We can write at a lower bit rate. And when we consider BCI devices, healthy individuals can use them quite effectively. They can use eye tracking systems and BCI devices to communicate quite rapidly. We do tend to see a precipitous fall off in the group that can truly benefit from using a BCI device. So these distinctions here, what we term ALS-LIS, is the locked-in state, where an individual is able to move their eyes but has no other functional control over their limbs or speech. And then in CLIS, which is the completely locked-in state, they've lost eye movement as well, where an eye tracker wouldn't work either. I would love to show that we've got BCIs that effectively work here, but if they do work, they're working extremely slow, meaning, a yes-no choice every minute. So the limitations for why we don't see more BCIs in the homes of patients with ALS are what I think are these threefold. The ability of the person to understand and perform the task, and I'll get into that a little bit and how we're planning to overcome those limitations. Accessibility, of course. We know that if eye trackers are $15,000, what can a BCI cost? It's going to be more than that, and currently there's no companies that are providing that. And then the limitations of technology. I use EEG in most of my research, but I'll talk about the drawbacks of EEG versus other technologies that we can use to record brain activity. So I want to focus a little bit on what determines whether someone can use a BCI, and can we find the resources outside of research, which is where BCIs have purely been studied, to bring them into people's homes. I think this was discussed by Gail earlier today. The different features of ALS, it's not purely a physical disease. There are also known to be cognitive and behavioral deficits that occur in about half of patients. So we've got the physical signs, we've got cognitive changes that may occur, and then as you can see here, there are genetic linkages that link FTD, which is frontotemporal dementia, to ALS. So we know from genetics that these can be quite overlapping. So when I initially started working with Dr. Simmons, who is the head clinician and the director of the ALS clinic at the Hershey Medical Center, that was what I wanted to focus on. The cognitive aspect of the disease wasn't considered as part of BCI research. So one of our publications early on is where we recruited 25 patients who came to the clinic, as well as 15 controls, and we had them perform these two tasks, the P300 and the motor imagery task. And we assessed their demographic factors, their cognitive factors, and their physical function as well. And you can see that you probably can't see the details of this, but it shows how accurate they were at using the P300 system, which much more people were good at using that system. It's something you can get the grasp of quickly. It doesn't take much practice. Whereas for the motor imagery system, it's like acquiring a skill. And some people were good at it right off the bat, and for others, it takes a little longer to learn how to do that. What we did show was that in alignment with the literature, about 14 of the 24 people that we performed cognitive testing with fell below some threshold to indicate that there was some cognitive impairment there, typically in the form of attentional executive functioning, so ability to keep sustained attention to a task. And we found out more than any other factor that low cognition score affected performance. You might think, well, duh, if they're not paying attention to it, they're not going to do as well. But this is something that hadn't been considered prior to this in terms of BCI research. We also went very out of my comfort zone and looked at how a common expansion of a gene in ALS, the C9 on the C9 chromosome, was correlated with BCI performance. So we took our cohort that I looked at, that I talked about earlier, our 25 patients, and in collaboration with researchers within our institution, they sequenced the expansion length of this gene, and they looked at who had an expansion of the C9 ORF gene. And we had 4 people who had this expansion and 21 who didn't. And what we found was that the people who had the expansion did worse on the using the BCI system. And the reason that we think the reason we think that this was the case is because it was tied to their cognitive ability, since FTD and ALS are known to be linked by this common gene. So yes, we found that this is a limitation, but how can we overcome this? So our next study was to look at a variation of the P300 Speller that might be able to overcome the limitations that we see for people who might have attentional deficits. So instead of flashing a letter, which is what we were typically doing with that grid of flashing letters, we flashed a face instead, as you can see here. We thought, this is a much more salient object. There's evidence in the psychology and neuropsychology literature that flashing faces as a stimulus produces a more robust evoked potential that we can use to classify. And when we looked at the 2 groups of patients, and I guess I should describe that the blue line here is when we flashed the faces and we performed the P300 spelling task using face stimuli, and the yellow line is when we used the classic stimuli. We see a huge effect in these central channels. So CZ and PZ are right over the midline, called the vertex, and we see an enhancement of this vertex potential, which we were expecting. We also see an enhancement of this N170, and these are technical details about neurophysiology, which nobody needs to know, but these are both face-specific potentials, so it made sense that we were seeing enhancements here. The important piece is that we also saw functional improvements in patients. So the people who did, so on average, people were getting 55% accurate, and that was bumped up to about 65 when we used faces instead of the classic flashing letter stimuli. And notably, the classic speller, which we know fluctuates with cognition level, was shown to be a function of cognitive score, whereas for the face speller, we didn't see those strong upward trends, meaning higher cognition, better performance. So the faces, this is evidence that the faces might bypass some of those attentional limitations that we see. The other piece is the piece that was briefly mentioned about the funding we got through the ALS Association to put these devices in people's homes. So getting them to use them on a daily basis or a weekly basis instead of having someone come to the research lab and go through the process of doing that. So with the funding of the ALS Association, we were able to purchase a few of these systems where I would stick it in the person's home. They would be used by the user, this is the patient, and the operator, which was usually a caregiver. In practice, it could be used by an AT professional, but I was coaching them as part of the research program using our telemedicine system at the Hershey Medical Center. So over the course of 8 weeks, we would video conference. I wanted to say Skype, but we don't use Skype. We would video conference with the patient and the caregiver in their home. We would go through the process of setting the system up, using it, and we wanted to track how efficient everyone got at using the system, whether performance improved, to kind of give an indication of how usable are these in the homes of users?
Lose your capacity to concentrate,
Yep.
which is, it takes full concentration at all times. Especially, you're not allowed to move your eyes. That's
Yeah.
not what it's all about. You're sitting there, pardon me, staring at a screen and making a notable response to your, excuse me, a notable response to your, to what you're seeing only in your mind. And it becomes challenging after about 35, 40 minutes.
So I think, I completely agree. I've done this task myself a number of times, and I experience the fatigue the same way you experience the fatigue. So I can only imagine it's a little bit worse for you.
Well, and yeah, and the sitting still, not being able to move. Now, yes, you can adjust yourself between sessions or between actions, but you always have to be centered on the screen. If you move too much, you have to redo the eye
Yeah, the calibration of the eye.
calibration that you're sitting centered to the screen, and you're constantly in concentration at all times.
In terms of fatigue and just general interest in using it, this is a simple interface, right? You're looking at this black board of letters. I think the integration of augmented reality, for example, might alleviate some of that. You're being presented with what looks like a game rather than a simple letterboard.
I enjoyed doing it. It was just, it wore you out after a little bit.
You're not alone.
Thank you.
These days, there's so much money's being put into artificial intelligence, and there seems to be some relationship to what you're doing here. It's, would you maybe talk a little bit about that, or?
You're right. There is a lot of money and a lot of research being put into artificial intelligence. It's certainly, I don't call it artificial intelligence in my work because I'm not using any of these newfangled paradigms at this point. I call it machine learning. It's how you can take a signal that doesn't make any sense to a human, but you feed it into a machine, and it can make sense out of patterns and classes from that. And that's exactly what we're doing. But I think the revolution that's occurring in artificial intelligence can do nothing but help our classification here. Thank you very much.